Today's notes are called independent events. Yesterday we did the addition law of probability, right? And what we did with those is we talked about if you have to say the probability of A or B, your job is to add the probability of A and probability of B, but then subtract the probability of overlap. Independent does not mean no overlap. That's not what that means. No overlap is mutually exclusive. That's no overlap. What's the other term for it? Disjoint. So disjoint and mutually exclusive means no overlap. That is not what independent means. And please keep those two ideas completely separate from one another. So what are independent events?
You're not sharing your screen.
I'm not sharing my screen, which means these notes are completely borked. Oh, that's not true. Only you can't see the screen. That's right. You guys can just guess, okay? There you go. Sorry. What are independent events? Independent events are events that don't care about the results of the other one. For example, I flip a coin and I roll a die. The coin is unaffected by the die, and the die is unaffected by the coin. These two events are independent. Every time your parents have a child, technically there's a 50-50 chance of a boy or a girl. It doesn't matter if you've had 6 boys in a row, the next one is 50-50 chance because they're independent events. I like roulette, even though I know it's a bad game to play. Every single spin is completely a brand new spin. Doesn't matter what's happened in the past. It doesn't matter that 16 red numbers just fell in a row. The probability the next one will be red is near 50-50. Say near because it's not even, it's not a 50-50 shot. But the point is it's close. It doesn't matter that it's happened 16 times in a row. Independent events are unaffected by one another. If A and B are independent events, then the probability of A and B happening is the probability of A times the probability of B. Now, before I get into this example, I want to talk about what that means with relationship to yesterday's material, because I told you all these things by themselves, easy. Once you start putting them together, well, yesterday's addition law of probability.
So wait, what is the other meaning again? It's not and. It's
I'm sorry, that means union. It's or. It's an or statement. The union symbol is or, and the and symbol is intersect. I'm writing this formula from yesterday's notes because that intersect symbol, like Kennedy just asked me, the intersect symbol means and. So if they're independent events, then at the end of that statement where it says probability of A intersect B, if you are told they are independent events, then that is the probability of A times the probability of B. So this is only true if you are told independent events. This is only true if they explicitly say independent events. So yeah, we'll mix these things a lot. Now, if you've got a Venn diagram, well, you can just count, right? But sometimes you're just given numbers. A coin and a die. Hey, look, it's almost like I knew what these notes said. A coin and a die are tossed simultaneously, but they are still independent, separate events. It says determine the probability of getting a head and a 3. Okay, well, what's the probability of a heads? Yeah, 1 over 2. And what's the probability of getting a 3? 1 out of 6. So what's the probability of both events happening? The probability of a heads and a 3 is 1 over 2 times 1 over 6, which is 1 over 12. That's pretty easy, isn't it?
Wait, how did I didn't know you use that formula for
What? Yeah, the multiply. And is done through multiplication. So or means add in some fashion. You have to remember sometimes you need to subtract and overlap. And means multiply. Which is why I brought up the additional law of probability from yesterday, because the additional law of probability has an and statement in it at the very end of it. So you would need to be told, are these things independent or not? All right, Carl, poor Carl, he's not having much luck lately. Carl's car only starts 80% of the time. And his motorbike, instead of saying motorcycle, maybe it's like a scooter, his motorbike, his Vespa, will only start 60% of the time. Man, this guy needs a new car. Part A says to draw a tree diagram to illustrate the situation. Okay, so let's use tree diagrams, and they are finally going to be useful to us. Event 1. And you don't have to label them, so you know what? I'm not even going to label it, screw it. Event 1. Your option is he's either going to how do I want to do this? Okay. Draw my branch. Event 1 has 2 options. Those options are, what is it, car and motorbike? Car and motorbike. And then what we mean by event is, let's just say, for some reason, Carl likes to walk outside and attempt to start both of his vehicles. Because it's just gas and starters, right? Who cares? Let's just start them both. Or try to start them both. Because Carl is a nerd and he just wants to know about probabilities. Okay, so Carl goes out and he attempts to start both his objects. Let's just say he tried to start the car first. Right? Well, let's see, I don't want to do this. Okay, let's do it differently. I'm going to basically invert the tree diagram. I want to do it a different way than I was about to, so hopefully you didn't write in pen.
Thank you.
But just go with me with this, okay?
No.
Let's pretend Carl attempts to start the car first. It actually doesn't matter, okay? Let's just say he goes to start the car first. Let's let C mean car starts, and let's let C prime mean C doesn't start. Car doesn't start. We cool with that? Because the prime symbol means not? Comfortable with that? Okay. So event 1 is Carl walks over to the car and he turns the key, or he presses the button if he's got a new car. And car either starts or it does not start. Then, regardless of what happened with car, Carl walks over to other object, which is motorbike. Motorbike either starts or doesn't start. So M or M prime. And like I said, regardless of what happened with the car, the motorbike either starts or does not start. Yeah, this is better than what I was going to do.
This one's kind of a hard tree diagram. This one's kind of like a hard.
Well, the way you have to think about it is you have to think about the 2 different vehicles are the separate events. And for each vehicle, 2 options happened. So that's how you have to think of it. Now, could I have done motorbike first and then car? Sure, it doesn't matter. The order is unimportant for this one. That is one thing that's really nice about this level of mathematics for IB. Order won't really matter for us unless you're specifically said, in this order, which is a nice thing because combinations are much easier to deal with than permutations. But anyway, yeah, so it didn't matter. You could have said motorbike first or car first. And the event is, does the car start or not? Does the motorbike start or not? Yes, Gavin.
Last night on homework 13 on one of the questions, it said for 3 chances of a girl, a boy, and if you're gonna have kids, and it asked for the probability of it said girl, boy.
It says in that order.
In that order, not just 2 girls and 1 boy.
Yeah, that's not what it said. No. Otherwise, they would have said, what is the probability of having exactly 1 boy? Because then it can happen more than one way. But if it says girl, boy, they dictated order. There's only one way that can happen in that order. Okay? So, all right. Now, this tree diagram, the way it's drawn right now, and like I said, when we were going to use tree diagrams where they're useful to us in a situation like this, where we do not have equal probabilities of things happening. So the probability that our car starts is 80% of the time is 0.8, right? So what's the probability that it does not start? 0.2. Notice that these two branches add up to 1 because an event either happens or it does not. Now, regardless of what happened with the car, the probability that the motorbike starts was 60%. That's 0.6. So starting is 0.6, so what's not starting? 0.4. And again, those branches come down here with the exact same probabilities. So the really nice thing about a tree diagram is if I wanted to know the probability that the car started first and then the motorbike started, all I'd have to do is multiply down the branches. So it would be 0.8 times 0.6. And you notice I was very specific to say and then, which means I dictated order. Now it says use this tree diagram to determine the chance that both will start. That means car starts and motorbike starts. So how about, I'm going to cheese this a little bit and I'm going to use some highlighters. Let's do both will start in yellow. Both will start in yellow. So, I'm sorry? 0.6 and 0.4? What are you asking? Oh, I thought you were asking me a question. Here's the probability that both start. That probability of oh goodness, I'm still writing in highlighter. The probability, that's better, of C and M is 0.8 times 0.6 or 0.48. So there's a 48% chance that they both start.
Since the original problem was in percent, will you have it change that to a percentage, or can you just leave it like that?
You know, just because it says determine the probability or the chance, you can use percents, decimals, or fractions.
Okay.
Part I, which I'll do in, how about fuchsia? Fuchsia feels good. Fuchsia highlighter. Carl can only, that's blue, come on. Fuchsia. Carl can only use his car. That means car starts only. Car starts only happens here. And, oh, that's it. That's the only time where car starts only is right there. So the probability of car only looks like conely. I should have said only C, is 0.8 times 0.4 or 0.32.
Wait a minute.
Wait a minute, what?
That doesn't make sense.
That doesn't make sense?
Only uses car.
Yeah, that means his car worked, but his motorcycle didn't. That's why I followed that branch. That's the branch of...
Does that mean he only tried his car?
No, Carl can only use his car. Remember, Carl went out and tried to start them both. So we're asking, what was the probability that car started and then motorbike didn't? And there was a, Gianna had a question.
Can the notation be C cap M prime?
Yeah. So I could have said probability of, oh, I like how you said cap. C intersect M naught. Yeah, that's what it's called. It's called a cap. But yeah, C intersect M naught. Yeah, that's good. Was that what you were going to say? Oh, wow. Great minds think alike. But yes, perfect. So yeah, Alberto, the words, we have to kind of read into them a little bit. If it says he can only use his car, because remember, he went out and he tried to start them both because it's just money, right? Who cares if we're burning gas? And we were like, oh, well, my hand was forced. Car's the only one that started. Okay? So this is the real power of a tree diagram. Useful this way, aren't they? Yes, Ms. Rep. Great. I'm glad you see it my way. And the last example for today. Liam rolls a 6-sided die twice. Determine the probability that exactly 1 4 is rolled. Okay. So what you have to do for this one is you have to remember that each roll of the die is an independent event.
Oh, that's horrible. That's such a...
Yes. 1, 2, 3, 4, 5, 6. Goodness.
Oh, this is gonna be great. Do we have to start them all at the same point, or can we just do it like
Well, I mean, you could do.
like
I mean, we could. How about we do this? Maybe this would be easier.
yeah?
1,
Yeah. Thank
2, 3, 4, 5, 6, and then just branch them from there.
Yeah. God, I'm a genius.
Is it 10 over 36?
I'm sorry?
Is it 10 over 36?
Well, I don't know. We're about to find out.
Wait, why can't you just do? I don't understand why you do the drawdown like. You know how you did the one time, like on the other side, we just multiplied 1/2 times 1/6 for that.
So I want to make sure that question makes it to the notes. So you were asking me, why can't we just say the probability of
It would be 1/6,
1/6 because it's a 4,
and then it would be 5/6 that it's not a 4.
5/6 that it's not a 4. And then that would give you 5/36, right? Okay. Gianna, you asked me if the answer was 10/36. How did you get that number? Because she just said 5/36.
So, if the first event, if you get a 4, there's 5 possibilities that you won't get a 4 again.
Right?
And then if you go to every other number, there's 1 chance you'll roll a 4 for each one. That's number 5.
Okay, the way you just said that must have worked in your brain, but it made no sense to me.
Yeah,
So I'm not going to attempt to repeat that in my microphone. Instead, what I was really hoping you would say was either the first one rolled the 4 or the second one rolled the 4. And when you say the word or, you add from yesterday's notes. I was going to use the tree diagram to demonstrate that this happens 2 different ways. It doesn't take too long. There is use in proving why it worked, rather than me just going, remember, it could have happened 2 different ways. If you draw the tree diagram, now you understand it better. It makes good notes. Would I have drawn the tree diagram for this? No. God, no. I would have done exactly what Kennedy said. I would have done 1/6 times 5/6, but then I would have multiplied by 2 because I would have realized that it could have happened in more than one way. Now, asking students to understand that without seeing the tree diagram often doesn't work very well. Okay, so that's why I wanted to draw the tree diagram. And yes, is the tree diagram kind of difficult to draw? It is. Nobody's going to lie. Okay, it's kind of hard. So let's see if I can pull it off. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh goodness. 1, 2, 3, 4, 5, 6. Oh gosh, it's not going to work. Ah! I'm running out of space. It's not impossible. It just needs to spread out so much more.
This is a joke, right?
No, you didn't hear any of the explanation that I just went through because you were talking, weren't you?
No, I know, but like.
What? You know what?
We have to do this, but like, there has to be an easier way to.
There is an easier way, and I already told you what the easier way is, Gavin. Did you hear it? No, because you were talking.
Lies, you're lying. Sorry.
So on and so forth. Can I just write etc.? Can I just write etc.? Will anybody care if I do that? You guys get it? Okay. How about this? Let's do it like this. Let's go down each branch and let's figure out how many times we would have rolled a 4 on that branch. Let's do it like that. And again, this is not how I would have done this question. It's just how I'm showing you to do it so you don't have to just trust me, because I hate telling students just trust me. If we rolled a 1 first and then a 4, there's 1. If we rolled a 2 first and then a 4, there's 2. 3 first and then 4. Now, let's just... I hate that. I keep forgetting to switch inputs. Let's assume we saw all 6 numbers, but we only saw the 4 there. Let's assume we saw all 6 numbers, but we only saw the 4 there.
This makes sense now.
Yeah. Oh, God, again. I can't.
I'm glad you never write this way because honestly I didn't really know.
That's why I draw the tree diagram. Does it suck? Yes. Okay, it really, really does. Now, those 1, 2, 3, 4, 5 branches are you rolling the 4 with the second die. Now, that I skipped over what if I rolled the 4 with the first die. And again, I'm just gonna kind of spread the numbers out over here, okay? And let's see. Sorry about my tree diagram, guys. 1, oh my God, I hate life. Oh my gosh, somebody kill me. All right, 1, 2, 3, 4, 5, 6. Okay, now my tree is getting a little, my grandmother would say leggy, meaning its branches are getting a little out there, but it was the best I could do. Okay. So for this one, I'm only gonna highlight where I rolled the 4 one time because it said exactly 1, 4. Well, God, kill me. All right. Oh my gosh. No! I'm pressing the wrong button. Oh my God. Okay, I swear. Okay, Goose Fraba. There's 1. There's 2. There's 3. I can't do 4, 4 because that breaks the rules of rolling it more than once. There's 4 and there's 5. So there are now 10 golden branches when there would have been 36. So you see that there is a 10 out of 36 chance of the It'd be funny if it was like on purpose, but at this time it's just like it's not. Probability of, so how would I want to say 6 and not 6? Or 4 and not 4. But then I don't care about order. I'm just going to write only 1, 4. Only 1, 4. 10 out of 36 because 36 chances total. 6 times 6. There's 36 total options. And if you were to go through the whole big tree diagram and highlight the times where exactly 1, 4 happened, you're going to get 10 branches. So there's 10 out of 36. Of course, we could reduce that to what? 5 out of 18. Okay, whatever. Now, what's the fast, easy way, Gavin?
Yeah.
Put the phone down. Maybe you'll hear the shortcut the second time I do it. I'm glad that's making it to YouTube. The shortcut. There are 2, and so this is the end of your notes, right? So I have space down here?
Yeah.
Okay. Let's do it like this. What is the probability of 4 and not 4? The probability of a 4 is 1 out of 6, and the probability of not a 4, 5 out of 6. This is 5 out of 36. Or, which requires us to use yesterday's notes, the addition law of probability. What if the first one was the not 4, but the second one was 4? Not 4 has a 5 out of 6 chance, and the 4 has a 1 out of 6 chance. So there's another 5 out of 36 right there, and when you add those, you get the 10 out of 36. Or even faster. Realize because there was 2 die, there were 2 different ways this could have happened. So you go, okay, the 4 and the not 4, that's 1/6 times 5/6, but that can happen in the reverse order, so times 2. And that's how you get to 1036. It's the fast way. But the tree diagram is what really allows you to see that that is what's happening. And if you need to draw a tree diagram, you do. But if you don't need to because you understood the fast, easy way of doing it, awesome. And that's it.
And you can draw the shorter